Hey folks, so in this video I'll introduce the idea of the fantastic four approach for designing recursive methods. So what are we talking about this? What are we going to do this? Basically, right, sometimes when people are using recursion they run into trouble knowing what exactly they should do. And so fantastic four is basically a list of four things that if you do them, you should be able to get a recursive function that works, that does what it's supposed to do. So to me, it's kind of like a scaffolding approach to be like, oh, if I do these steps right, I'll get all the bits and pieces that are important for recursion. So that's what we're going to go through. We're going to go through the different kind of parts of Fantastic Four in terms of doing factorial, which is very simple, but really just for illustration here. And later on, we'll do a couple more complicated examples using Fantastic Four to show how it can be used in more scenarios. All right, so let's take a look at these four steps. So the idea, right, is I follow these four, right? So it's like I have an algorithm for creating recursive algorithms. Okay, how about that? Except this algorithm isn't for Java, it's for me or for you. All right, so we're going to try and implement factorial. So we're going to go through these four steps, and we're going to talk through these one by one. Let's take a look, though, at an overview real quick. First thing is we need to figure out the size n problem, which means like the whole problem. We need to find the stopping condition and return value. This is really, well, these things together make up what I typically call the base case. Again, base case is the term in induction from math. So number three. Formulate the size m problem, right? So this is the subproblem. Find m, that's kind of like meh. And this is like wishful thinking here. In many cases, m equal n minus 1. This is if we're doing something that's like numerical, like we're calculating a factorial, okay? Yeah, the subproblem is n minus 1. Easy. Also not very useful to us in the future because we want to solve problems that aren't trivial, right? We want to solve real problems, not just, computing factorial. We'll just use it here, though, because it's, a simple example to start with. The last step is to construct the solution of the problem right from the subproblem. So it's like, well, we know what the full problem looks like. We know what the subproblem looks like. What is the glue the holes in together, right? What is a little bit of work I need to do to the subproblem to get it to be the whole problem? So that's my number 4 here. All right. Let's see. So yeah, we're gonna do factorial. So step 1, right? Formulate the size n problem. So basically, right, I want to think about using recursion, right, when I have a problem where it's like, well, I need to do the same thing over and over and over again, right? I need to repeat things. Basically, I use recursion when you use a loop. So what about factorial? Do I need to use recursion there? Well, probably, right? So a factorial is something like this, right? It's like, well, I have maybe 6 factorial, that's the way I'd pronounce it. And that's equal to, 6 times 5 times 4 times 3 times 2 times 1. Great, okay? So I have these things all drawn out, right? I'm kind of repeating this thing. I'm multiplying. That's why maybe I think about using a loop, or here I think about using recursion. All right, so recursion seems to be the way to go to solve this factorial thing, right? Basically write a recursive method to calculate it. So what should we look at doing? Well, first of all, what we need to kind of identify is our problem size. So here, right, I have this, and somehow, right, our problem size is really our factorial size, right? So our n is like the number we're taking the factorial, right? So that is our problem size. And here, right, we can just literally leave it as n. It's nothing, complicated. It's really just n. So yeah, computing the factorial of n. So computing n factorial is basically, n is already given directly. So we know what the problem size looks like. How do we, determine what the whole problem is? Well, in this case, what we'll do is we'll basically just have some wishful thinking. So we're going to write a method name, which is the method that I would have if I had solved the problem already. So that's actually this here. So I'm just making this up. It doesn't exist yet. Int factorial int of n. So the number I'm taking the factorial of is the parameter. The return type is integer, right? This is what my finished product will look like. I don't have it yet. I'm just going to assume I will. I will use that assumption in another step. So that's what I have, right? I start with that. All right. And I can kind of figure out, from the return value, right, is from what I want to get, right? So this is, I don't know what this ends up being, 36 times 20. So like, I'm going to guess that's like 720, but I don't trust my math. So that's probably 720. Point is, right, it's an integer. So it makes sense for my return type to be an integer. And I already know that my factorial I'm taking is going to be an int, right? And it's called n. So yeah. So this leaves us basically with a method signature for, this is how it would look when it's done. And we'll use it again in a minute. All right, so find the stopping condition return value. This is kind of step 2, okay? So you can kind of think of this kind of being related to like a while loop. In a while loop, right, you have things like this. Well, blah, 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 and then inside you have some code. When you have something like this, basically what it is, right, is that you have, this conditional, and over here it must be checked before you go and you do the body of it. so that you don't do it too many times. Same thing with recursion, right? We need to have some sort of a check to see, what is it that are we at the point where we want to stop or not? So we have that, right? So if if our condition basically ends up being true, that means we want to return a corresponding value, right? We have something, to give back to the user, if you would. Note that sometimes I say user when I really mean programmer. I've been on kind of this side of the fence so long that when I say user, it's like who's using the program, like in terms of like the programming language, not the person who's using who you're shipping to, which is a little bit weird, but that's me. So, all right. So we want to identify our stopping condition and our corresponding value. Well, basically the question there somehow is, for factorial, what is the simplest possible factorial I could ever take the factorial of, or number I could take the factorial of? Well, that's going to be 0, right? So basically, my stopping condition, right, is going to be when n equals 0. So when I get to the very smallest factorial, I'll stop. And when I stop, I'm going to return the value 1. Okay, so that's my stopping condition, return value. This is also looking a little bit like, and I'll just draw this on the side for a second, the mathematical definition for a factorial. So the mathematical definition for factorial is this. So n factorial equal n minus 1 factorial times n. And I guess over here I should put 0 factorial equal 1. Okay? So this is kind of my definition for what factorial is in terms of math. So yeah. All right, so got my stopping condition, my return value. What's next? I got to talk about the subproblem. So subproblem, right, is basically that smaller thing, right? I want to have some smaller thing to work on. Well, here that's easy, right? Our whole problem is something like this n factorial. Our subproblem is this n minus 1 factorial. So that kind of jumps out at us immediately. In general, right, we want to make sure that m is always smaller than n. We already kind of talked about that before, this idea of progress. And you can see that directly here, right? I have n versus n minus 1. Obviously, n minus 1 is going to be smaller, okay? So we know we're reducing the problem size. All that is good. Let's see. So we have basically, right, this is our subproblem. Now what we want to do is basically phrase the subproblem in terms of that method that I first talked about in part 1. I said, oh hey, the final result would be factorial of n. Well, in terms of that, the way we'd solve the subproblem is we say, okay, I would need to make a call to factorial of n minus 1. So this is actually my subproblem, right? My subproblem is the work that's inside to do. The work that's inside to do, thinking back about the recursive definition, the work inside to do, right? So this is the whole problem. This is your subproblem. Well, then your work inside, right, is basically to call factorial of n minus 1. So that is our subproblem there. All right, and when we rewrite this, right, we are sort of in a sense basically assuming that it's legit to do so, right? That factorial somehow exists already, right, or will exist right when we're done. All right. Now later on, basically so the next step to talk about basically is going to be in terms of how do I take this size m subproblem and combine it with my whole how do I do some work, right, in order to get out that whole size problem. All right, before we get there, just some notes here. It's not always as simple as n minus 1 when we're looking at subproblems. Some examples which maybe are familiar to you. If you've seen something like the merge sort algorithm, merge sort is some sort of algorithm, right, where it's like we break an array in half. N basically ends up being one half each time. Or if you're taking this class in a semester with the maze homework, you're actually breaking your initial maze right into 4 pieces, which is m equals 1/4 n. So your kind of your breakdown can be a little bit different. What's really important is this bit over here, right? Is that no matter what, n is less than m, right? That's what matters. Could be minus 1 divided by 2 divided by 4. Just as long as it's smaller, life is good. All right, so let's take a look at how we combine the subproblem with a little bit of work to get out the whole size problem. So we're basically going to assume that it would be legit to write a bit of code that has the usage of the first outside function, right? The main thing that we're trying to implement. So even though we haven't done it yet, we're going to assume it exists and then use it to basically construct the inner solution. So in that case, actually, it's pretty straightforward. Factorial of n minus 1 times n, right? Done. So this is basically, right, and I'm already on the side, factorial of n equals that, right? Basically is what we're saying, right? The whole size problem, right, that whole factorial of n is equal to n times factorial of n minus 1. So this is my whole problem over here, subproblem over here. And this is a little bit of work that I'm doing. Because remember, before I drew the expression, right, and it was just for semantics, right, just for understanding, that the whole problem is equal to the subproblem plus some work, right? So that's kind of the breakdown going on there. All right, so that's got us kind of almost there. The last bit we kind of need is to bring everything together. So we have this idea of how this method would look like outside. How do we have it inside? This is kind of the main work going on, and also that stopping condition and that base case. So pulling it all together, we get this. So we have our size n problem here, right? Our function that would solve it. We have our stopping condition here, stopping condition, our return value, together base case. And I need to check this first, because if I don't check it first, well, bad things will happen. Bad things, you can maybe think about it on your own, but we must check the base case first for something like this. Over here, right, once we're done, we basically say, oh, hey, if I'm not at the end, return factorial of n minus 1, right? So basically it's like, well, we're doing kind of we're doing a little bit of work, right, this stuff here, and then deferring to recursive call. So if I were to do something like, for example, call this on, factorial. So let's say I did factorial of 6, which is one thing that I kind of drew up here before. What that ends up looking like is the following. If I call this code, I start by saying, oh, hey, factorial of 6, well, that ends up being basically 6 times factorial of 5, right? This is a recursive call, which ends up being 6 times 5 times factorial of 4, ends up being 6 times 5 times 4 of factorial of 3, ends up 6 times 5 times 4. This is where I'm regretting having such a large number. Factorial of 2, 6 times 5 times 4 times 3 times 2 times factorial of 1, which in the end gets me to 6 times 5 times 4 times 3 times 2 times 1. And then kind of you filter back up, and this is like the final result, right? So it's like functions have to call functions, have to call functions, have to call functions, until I get to the very end where it's like, well, the simplest thing is factorial of 1, or factorial of 0. I should have gone all the way down there to factorial of 0, but I don't have space on the slide. And then I have this entire expression. There's no function calls in it, and so the whole thing can be evaluated. So yeah, that's factorial. If you want to, you can maybe spend a little bit of time playing with this. Right? This is our mathematical definition. By play, what I mean is the following. There are things that basically will work out or not work out depending on how these formulas are written, right? Or this recursive thing is written. Somehow, right? This is sort of a summary of this up here, right? We talked through the code itself, right? But this is the mathematical definition, and they're very, very close. The program, right, just has some extra boilerplate on it because it's Java code. But if you want, you can play with that a little bit and maybe help to understand a little bit of an intuition that maybe is behind the scenes for when you specify something recursively. In any case, right, hopefully you have an idea now about using Fantastic Four. Remember, there's kind of 4 main steps, right? Find the whole size problem, find the base case, find the subproblem, then combine the subproblem with a little bit of work to get the whole problem, right? So as long as we follow those 4 cases, usually we stand a pretty good chance at coming up with a recursive function. Now, in the videos that follow, we're going to mainly be talking about different examples of actually using this Fantastic Four approach.